DeepSeek says it was hit with a large-scale cyber attack.
An AI hedge fund side project, DeepSeek, that wiped out $1 trillion from the US stock market, recently got hacked. Its sudden rise in popularity has spread shockwaves throughout the AI world, not just for its performance, but also for the cyber catastrophe that exposed its Achilles heel just weeks after its release. Today, we'll seek deep, pun intended, into how this attack was carried out and what implications it has on the future of LLMs such as DeepSeek. But first, what is an LLM? An LLM, or large language model, is a type of artificial intelligence system designed to understand and generate human-like text. At its core, an LLM is a sophisticated mathematical function that predicts what words come next for any piece of text by assigning a probability to all possible next words, and the word with the highest probability rating is chosen as the output. However, rather than processing entire words, LLMs break down text into smaller units called tokens. Tokens can be words, subwords, or even individual characters, depending on the language model's design. For example, the word artificial might be treated as a single token, or in some models, it might be broken into arty and official for more efficient processing. This token-based approach allows LLMs to handle diverse vocabulary, predict missing words, and generate text fluidly. The process of token prediction is repeated iteratively, allowing the model to generate coherent and contextual responses. LLMs are built on deep neural network architectures, most notably the transformer, which uses a self-attention mechanism to weigh the contextual relevance of words throughout a text. During the training process, these models are exposed to vast amounts of data from books, articles, and online sources, enabling them to learn grammar, context, and the nuances of language. This training occurs in two key phases. Pre-training, where the model develops a broad understanding of language by predicting the next word across diverse data sets, and fine-tuning, where the model's responses are adjusted for a specific task and use cases by modifying its parameters. In this context, parameters are the numerical values, essentially the weights that the model adjusts during training to improve its accuracy in understanding and generating text. Each parameter helps to determine how strongly words in a sentence relate to each other, how different language structures should be interpreted, and how the model predicts the next token. The more parameters a model has, the more complex relationships it can learn. But this is also significantly increases computational costs and energy consumption. So what makes DeepSeek better than some current LLMs? Unlike traditional transformer-based models like ChatGPT, which activate all parameters for every token they process and typically rely on tens or even hundreds of billions of parameters, DeepSeek version 3 employs a mixture-of-experts architecture. DeepSeek has a staggering total of 671 billion parameters. However, DeepSeek version 3 activates only about 37 billion tokens instead of engaging the entire model at once. This selective activation reduces the computational burden while maintaining high performance, making it far more scalable and cost-effective than models that require full parameter usage. Full parameter usage means that every single weight in the model is activated and processed each time the model generates text, leading to high computational demand. This constrains server resources, increasing latency and dramatically raising operational costs, especially in cloud environments where AI models run on GPU clusters or specialized AI accelerators. OpenAI's ChatGPT model, for example, requires hundreds of millions of dollars in compute and infrastructure costs to develop and deploy at scale. DeepSeek's MOE approach, by contrast, reduces this strain by only activating the most relevant subset of parameters, allowing it to achieve similar or sometimes even superior performance while requiring way less power, storage, and processing capacity. What makes this even more impressive is that DeepSeek was reportedly developed for just $6 to $10 million, a fraction of the cost it took AI to develop the ChatGPT model, proving that optimized architectures can deliver high performance without breaking the bank. DeepSeek's innovative design not only redefines efficiency in handling complex token probabilities, but also sets new benchmarks in AI performance and cost. Yet, as its revolutionary capabilities captured global attention, they also made DeepSeek a prime target for cyber threats. Just weeks after its meteoric rise, a sophisticated set of cyber attacks exposed critical vulnerabilities in their infrastructure. So what exactly happened? DeepSeek's downfall didn't happen all at once. It was a carefully executed assault that unfolded in multiple stages. The first sign of trouble came in early January, when the company faced its first wave of distributed denial of service DDoS attacks. These attacks are designed to overwhelm a target with so much traffic that it can no longer function properly. Often these attacks use botnets, a network of hacked devices, anything from smart cameras to home routers, that are hijacked and controlled remotely by cyber criminals. Instead of relying on a single source of attacks, botnets allow attackers to strike from thousands, sometimes millions of different locations at the same time. In DeepSeek's case, much of this malicious traffic originated from compromised devices in the United States, the United Kingdom, and Australia, making it clear that this was a globally coordinated attack. At first, the attacks used reflection techniques, which are particularly dangerous because they amplify the volume of malicious traffic. The attacker exploited Network Time Protocol, NTP, a system that normally is used to synchronize clocks between devices. Vulnerable NTP servers were tricked into sending disproportionately large responses to DeepSeek servers, causing them to become overloaded. At the same time, the attackers took advantage of the Simple Service Discovery Protocol, SSDP, a protocol designed for networked devices like smart TVs and routers to discover each other. By manipulating SSDP, the attackers directed massive amounts of data towards DeepSeek, making it nearly impossible for the company to keep up and keep their systems online. While DeepSeek's team managed to hold back the worst of the early attacks, this was only the beginning. As DeepSeek continued to gain popularity, particularly after launching of its R1 reasoning model, the attackers escalated their efforts. By late January, the attacks had evolved into something far more sophisticated. Instead of simply flooding the servers with meaningless traffic, the attackers shifted their focus to application layer attacks, targeting DeepSeek's web and API services. This method is far more difficult to detect because it mimics legitimate user behavior. Rather than brute force, these attacks overload DeepSeek servers by sending massive amounts of seemingly normal requests for web pages and API data. Unlike the previous waves, which could be blocked using standard DDoS protection, these attacks at the application layer blended in with real user traffic, making them significantly harder to stop. DeepSeek was left with no choice but to limit new user registrations, especially for those outside of China, in an attempt to stabilize its platform. But then came the most devastating phase of the attack. On January 30th, security researchers identified two Mirai-based botnets, HailBot and RapperBot, joining the assault. The Mirai botnet is infamous for hijacking vulnerable Internet of Things devices to launch large-scale DDoS attacks. Many IoT devices lack proper security, making them easy targets for malware. Once infected, these IoT devices follow hacker commands to send massive amounts of traffic toward a single target. So, this made DeepSeek's defenses nearly useless, as traffic was pouring in from countless compromised devices all over the world, and the scale of these attacks pushed DeepSeek's infrastructure to its limits, leaving little room for recovery. While DeepSeek was struggling against relentless waves of DDoS attacks, another, even more catastrophic security failure was unfolding in the background. On January 29th, cybersecurity researchers at Wiz uncovered a massive data leak within DeepSeek's infrastructure. This wasn't the result of a hack or a brute force attack. Instead, and rather embarrassingly, it was a direct consequence of a critical misconfiguration in DeepSeek's database security. The company had left its ClickHouse database completely open to the internet. without authentication, without encryption, and without even the most basic security measures. Wiz security researchers discovered that anyone with internet access could directly query DeepSeek's database using an exposed HTTP, Hypertext Transfer Protocol, interface. They identified two key servers, oauth2callback.deepseek.com and dev.deepseek.com, both running on unsecured ports 8123 and 9000. These ports led directly to a publicly accessible ClickHouse instance that required no credentials to access. When left unprotected, ports act as unlocked doors, allowing attackers to probe, access, or even manipulate critical systems. We also made a video about ports that you can check out in the description as well, in case you're interested. In DeepSeek's case, a simple show tables command revealed the extent of the exposure. One table in particular stood out, log stream, containing over 1 million highly sensitive records. These leaked data included chat logs, API keys, backend infrastructure details, and operational metadata. Everything an attacker would need to gain deeper access into DeepSeek's internal systems. Luckily, this vulnerability was found by cybersecurity experts and quickly reported to DeepSeek and patched. But this level of access exposed an enormous risk, not just for DeepSeek, but for its users. Anyone with knowledge of SQL queries could have exfiltrated plain text passwords, retrieved sensitive user interactions, or even modified data stored within DeepSeek's environment. Even worse, since the logs contained references to DeepSeek's internal API endpoints, attackers could have used this information to craft even more sophisticated attacks. DeepSeek had essentially left the door wide open, allowing anyone with the right tools to take whatever they wanted. This misconfiguration wasn't just a small oversight. It was a fundamental security failure that demonstrated how rapidly growing companies can overlook critical protections in their rush to scale. So, what can we learn from DeepSeek's mistakes? The main takeaway is that even the most advanced AI systems are not immune to fundamental security flaws. The sheer scale and complexity of the attacks highlight several key lessons for both AI developers and cybersecurity professionals. If a company pioneering AI can be crippled by a combination of DDoS attacks and botnets and an exposed database, then no organization is truly safe unless security is built into the foundation of its infrastructure. One of the most immediate lessons is the need for robust DDoS protection. The attackers behind the DeepSeek incident didn't rely on a single technique. Instead, they launched multiple waves of NTP, SSTP reflection attacks, application layer floods, and botnet-driven assaults. This layered approach allowed the attackers to continually overwhelm DeepSeek's defenses, adapting each time countermeasures were put in place. Had DeepSeek implemented multi-layered DDoS protection, such as rate-limiting mechanisms, intelligent traffic filtering, and real-time anomaly detection, it could have mitigated much of the damage. AI-based threat detection systems, which monitor traffic for unusual patterns and automatically block malicious requests, could have helped differentiate between legitimate users and coordinated botnet traffic. The role of botnets in this attack is another crucial lesson. Mirai-based botnets like HailBot and RapperBot were used to hijack Internet of Things devices, turning them into weapons against DeepSeek's infrastructure. This highlights the growing risk of unsecured IoT devices, which remain a major cybersecurity blind spot and issue. Many of these devices lack even basic security protections, such as firmware updates, strong authentication, or even the ability to detect when they've been compromised. Preventing botnet-driven attacks requires both device manufacturers and network administrators to take security more seriously. Manufacturers must enforce default password changes, disable unused services, and patch vulnerabilities as soon as they're discovered. Meanwhile, network administrators should implement firewall rules to block malicious IoT traffic, use intrusion detection systems, IDSs, to monitor unusual activity, and restrict access to critical servers from known botnet command and control servers. Perhaps the most damaging security failure, however, was the exposed ClickHouse database. Unlike the DDoS and botnet attacks, which required sophisticated coordination, this vulnerability was entirely preventable with basic security hygiene. DeepSeek's database was left open to the internet without authentication, meaning that anyone who found it could extract sensitive records, including, like we said before, chat logs, API keys, and backend data. This kind of misconfiguration is one of the most common security mistakes companies make. Yet it remains one of the most dangerous. To prevent such exposures, companies should adopt the principle of least privilege, ensuring that only authorized users and services have access to sensitive data. Proper access control lists should be enforced, requiring authentication and encryption for all database connections. Furthermore, automated security scanning tools should be deployed to detect misconfigured databases and other misconfigured systems before the attackers do. Regular penetration testing and routine audits could have flagged this issue long before it became a major security incident. Finally, the timing of the attack raises another lesson. AI companies, especially those experiencing rapid growth, must anticipate and prepare for cyber threats as part of their expansion strategy. This applies for any growing company. The attackers didn't strike randomly. They waited for DeepSeek to gain global attention, then launched their attack when the system was under the most stress. This pattern is common in high-profile tech companies, where cybercriminals exploit moments of peak demand to maximize disruption. Proactive security planning, such as stress testing during major product releases and building scalable cybersecurity measures alongside infrastructure growth, is crucial. The DeepSeek attack exposed fundamental weaknesses in security, from infrastructure vulnerabilities to poor access control. However, the incident also provides a roadmap for improving cybersecurity in any organization by deploying robust DDoS mitigation, enforcing strict database security, implementing network segmentation, and preparing for attacks as part of a growth strategy. Companies can significantly reduce the likelihood of falling victim to similar breaches. For more cybersecurity tips and resources, including certifications like CISSP, CISM, CCSP, visit devcert.com. And remember, just because an AI is popular doesn't mean it's secure. Stay safe out there.